one that we're looking right here has 92 balls. If I put on another layer, which I tried doing, then I found there was 162 balls. And I put on another layer, it's 252 balls. Every time I put on a layer, the number 2 shows up. I'm getting used to number 2 showing up now. That 2 will often have some very interesting significance. So therefore, it occurred to me, because 2 is common to each one of these, and this notation is decimal. It's called congruence in modulo 10. To count in rhythms of 10. And when there's an excess, a constant excess over the 10, like 2, for every statement, then algebraically you can treat it exactly as if the excess was, the 2 wasn't there. You can treat it as if it was 10 or 20, so forth. Therefore, I said I'm going to take off the 2 on each one of these, and therefore this will be 10 plus the 2, and this will be 40 plus 2, and this will be 90 plus 2, and this will be 160 plus 2, and this will be 250 plus 2. Then I saw each one of those is a multiple of 10. Therefore, I'm going to divide them arbitrarily by 10 right away. Therefore, I found this is 1, 4, 9, 16, 25 times 10 plus 2. I could say that the number here is always 1, 4, 9, 16, 25. What are those numbers? 1, 4, 9, 16, 25. This is a progression of second powers. First power 1, 2 to the second power 1, 1 to the second power, 2 to the second power, 3 to the second power, 4 to the second power, 5 to the second power. What we're saying here is that the numbers of balls, it will always be that. It's absolutely true. Then I'm beginning to discover, well, what is this? This will be going back to something I gave you a little earlier. Our friend the icosahedron, which is, remember, this is our 2-foot pole. Remember, 2 poles plus 2, which is the concavity convexity, times the prime number 5, which is icosahedron, which is our friend vector equilibrium and icosahedron are the same thing. In other words, this began to be a payoff to be telling me that the two-ness is always polar. And I discovered that every layer always has 2, which permitted then a neutral axis. And in a 4-dimensional system, you do have a neutral axis here. Each one of them can have an attraction to hold another 92 on it in respect to each one. Oh, excuse me. The outer set of balls always have the value of 2. And I'm going to give you a reason to know. No frequency. This is independent of size, vector equilibrium. While I see 3 balls here, there are 2 spaces, just 2 spaces between the balls. 1 space, 2 space. If I did this in a vector equilibrium, I would simply have to take it and break each of its edges into 2, making you see 3 balls, but it is really the number 2. This is a two-frequency geodesic, and you can't have less than 2 frequency. The word frequency begins with a minimum of 2. There's another kind of a 2 showing up. There's many kinds of 2s show up here. There's a 2 is a frequency phenomenon. Then I can, the next one will look like this. Sure enough, they go on layer after layer, and this is a 3-frequency phenomenon. There are three intervals between what looks like 4 balls and the external. Now, one of the things we learn about that, which is very interesting, is that, just open this up, we find that if you have 2 intervals on the circumference, then you have, look at any one radius, 2 intervals of the radius. Get down to x, y, z coordinate systems, and when you get to x, y, z coordinate systems, which will be the 3 axi of the octahedron, then the only way you know how to play game was in terms of linear subdivisions. And so you divided this line into so many increments, and you wanted to identify any point in space, and so you referenced it to the x, y, z coordinate system. You found that it was, you go over here to this one here, and then you found it was 4 increments out that way, and then it was say 4 increments out this way. You identify this point in space in the terms of the crossing of these lines and taking linear increments from modular subdivision. And one more in that particular account, that as we recede from the nuclear ball with which we started this, the red ball, that there might be unique patterns that develop in between the layers, and that they might get to the edges of 1, 2, 3, 4, 5, 6, 7, 8 balls, and that is a 7-frequency unit. It's a 7-frequency tetrahedron. I have a red ball at the top, which is then my beginning, my nucleus. It's the beginning of things. And you saw that the balls pack around economically in terms of 8 triangular faces and 6 square faces. We recognize that the squares are completely unstable. That's why it became the icosahedron. So it's only the triangular faces that are stable around.